The problem asks us to find the charge on every capacitor Q sub I, where I goes from 1 to 4, the voltage in every capacitor V sub I, and the stored energy U sub E on every capacitor. Now, I want to just recall to you some of the basic formulas involved in the subject. The capacitance of a capacitor is defined as a charge over the voltage, and therefore you can write the voltage as Q over C, or you can write the charge as C times V. The energy stored in a capacitor is given as 1/2 CV squared, and using C equals Q by V, you can also write this as 1/2 QV. I like this formula a lot. And if you want to eliminate V altogether, then you'll get Q squared over 2C. Any of these three formulas can be used to find the energy stored in a capacitor. Now, we have to find everything on all these items. So the best way to proceed is to draw a tree diagram, and that's what I'm going to do here. I'll draw the tree diagram of this circuit. In a tree diagram, the voltage is indicated on the top, and I'm going to use the triangular symbol for voltages. And then you go down, you're going to encounter, that's a positive terminal, you're going to encounter C1 and C2. So you draw them in the same order that you encountered them. Now, in between the capacitors, I'm going to put the value of the capacitance in microfarads. So my convention is going to be, wherever I put the triangular symbol, it's going to be volts. Wherever I put anything I put here will be in microfarads between the capacitors. If I have a charge, because it's microfarads, I expect the charge to be in microjoules, microcoulombs. And then the stored energy, you expect it to be in microjoules. So I'll use the box for the stored energy, circle for the charge in microcoulombs, and parallel plate capacitors have their values right in between the plates. So this is going to be 1. Then I have 2. On the other side, I'm going to encounter 3 and 4. And then it goes to the negative terminal, which becomes the earth. So the way you do the circuit analysis is to proceed 2 at a time. Now, I know that some of you can combine everything at once, but the idea is to only go 2 at a time. So I'm going to combine on the left side 1 and 2 in series, and on the right side also 3 and 4 in series. So I'll get a new tree diagram, the same 12 volts, but now it will only have one capacitor to the left and one capacitor to the right. Now separately, let's recall the formula for adding capacitors in series and parallel. The formula for adding 2 capacitors in series is C1 C2 divided by C1 plus C2. And the formula for adding 2 capacitors in parallel, CP, is just going to be C1 plus C2. Let's keep that in mind. So let's do the addition of 1 and 2. It's going to be 1 times 2 divided by 1 plus 2. So that's going to be 2/3. Here it's going to be 3 times 4 divided by 3 plus 4. 3 times 4 is 12, and 3 plus 4 is 7. Now what we have to do is add these two in parallel. So I go down to the smallest tree with just one element. In your homework, you may have to go in 4 stages, and in some other more complicated problems in 5 stages. But basically, the procedure is the same. Now, 2/3 plus 12/7 is what we need to add because they are in parallel. So I'll do that here. So the common denominator, I guess, is 21. And that's going to be 14 plus 36, which is 50, I guess. 50 divided by 21. Unfortunately, the numbers are yucky in these problems. So the effective capacitance is basically that. That's the effective capacitance in this circuit. Once you found the effective capacitance, you can find the total charge in the circuit using this formula. So let's label these trees. I'll call this one Roman numeral 1, Roman numeral 2, and that Roman numeral 3. And the idea is to work backwards. You go from here and hop your way to this one, filling in everything as we go. So let's do the analysis of the third tree. We can certainly find the total charge in the circuit from this. So I'll do that. Q equals C times V. The effective is 50 over 21, and the voltage is 12 volts. So that charge, this is farads, microfarads. I don't really care about the units unless you get the final units right. That's fine. 50, I have a calculator here, divided by 21 times 12. You can leave everything in fractions or approximate it by decimals. Leaving it as fractions is obviously more accurate in the problem like this. So I'll write the charge here as 28.6. Now, the voltage across a parallel combination is going to be the same. So the voltages can be immediately penciled in going back one step. So the voltage across this capacitor is going to be 12, and the voltage across this capacitor is going to be 12. What's not clear is how the charge splits. So we'll have to do that using our calculation for Roman 2. The charge is again given by, in this case, capacitor, this capacitance times the voltage. So let's do that. Let's say it's Q 12/7 is going to be 12/7 times 12, and that's going to be 144 divided by 7, which I'm going to write as 20.57. So you can see a lot of the same recurring fractions which comes when you divide by 7. So I'm going to get 20.57, which I'll write as 20.6. You have an option now to do the same thing for the other one, or simply subtract. Because charge is conserved, the total charge must be this plus this. So I'll just do 28.6 minus 20.6, which is 8. It's probably not exactly 8, but I'm just going to do that. Now, when you look at when you hop one step back, then you realize that the charge must be shared between two capacitors in series. Let's just revisit that argument really quickly because it's a very important thing to understand. If you look at this thing for a long time, you realize that the metal island shaped in the letter I is just floating around. If that's floating around, it must have no net charge. So whatever charge this has got, this has to have the opposite of that charge. And if you give this a charge Q, then that has to have a charge of minus q, because capacitors have equal and opposite charges on either plate. But if this island is neutral, then this also has to have a charge of plus q on this side, because if minus q goes there, you have plus q left on this side. Well, you're forced to conclude that this is going to be minus q. By this argument, regardless of the actual value of capacitance, you realize that capacitors in series must have the same charge. Long story short, each of these gets 20.6. And each of these gets 8. Now remember, when I say 8, I really mean 8 microcoulombs, because that's the unit system we are working on. Almost there. Now in this problem, there's nothing else to do. Well, okay, I have to find the voltage on each one. The voltage, the 12 volts somehow splits there, so that's back to the drawing board then. Roman numeral 1. How do you find the voltage? Well, using the same equation but turned around. V equals Q over C. So let's use that. Let's try to do the voltage on 3. V3 is equal to Q3 over C3, and Q3 is 20.6, C3 is 3. So back to my calculator. I get 6.87 volts, which I'll put in my triangular notation. I'll call it 6.9. Well, I can go and do the other one, but it's better to simply subtract, because 12 minus 7 is 5, so that's 5.1. Now we have to, because voltages add to the full voltage, we also have to do one of these, and then the other one can be got by subtraction in the same way. So let's do V1. V1 equals Q1 over C1, and that gives me C1 is just 1, so it's going to be, I should have, 8 over 1, which is 8. So that's 8 volts. And if this is 8 volts, then by subtraction, that has to be 4 volts. 8 plus 4 is 12. Observe this general phenomenon. The bigger capacitance always gets a smaller voltage in series, because they have to have the same charge. And you observe the same phenomena here too. Last item is stored energy. For this one, I like to use this formula. It's the best. 1/2 QV. In a diagrammatic parlance, U sub E is just 1/2 circle times triangle. So just grab the circle and grab the triangle and multiply them and divide by 2, and you're done. So let's do that here. That will give us an idea of the total charge. Okay, so 28.6 times 12 over 2 is just 6 times 6 is equal to 171.6. That's the total energy stored in the circuit in microjoules. Now we don't have to do the intermediate stages. Let's go to the end tree, the tree to the extreme left, and fill in the stored energies on these with rectangular boxes. Make these trees really big so they can fit in all the funny things. At the end, you can also put everything in a table, but I won't waste video time doing that table. You can do that in your homework. The table is already there. You just have to fill it in. So let's do the 1/2 circle times triangle thing here. 20.6 times 6.9 divided by 2. So I get 71.1. Let's do the same thing here. 20.6 times 5.1 divided by 2, and that's 52.5. So because these are already storing so much, you expect very little storage here. Let's see what happens. 1/2 circle times triangle, I don't need a calculator for this. 8 times 8 is 64, and so 64 divided by 2 is 32. And here it's 8 times 4 is 32, and 32 divided by 2 is 16. So as you can see, the energy stored in the smaller capacitors is always smaller. That goes to show that capacitance really has meaning. The small capacitance stores less capacity to store charge and hence energy. Now, the last final thing we need to do is to make sure that all this is self-consistent. By the way, this self-consistency check is not a proof that you did everything right. Even if you did a garbage analysis, it will work out because the mathematics is self-consistent garbage. So be careful. This is not exactly a acid test of self-consistency as much as it's an echo chamber of your mistakes. So let's try to see if 16 plus 32. But if this one is not correct, then certainly there's bigger troubles ahead. So let's try to make sure that at least these four add up to that. Whether we did the circuit theory wrong or not, at least that much should be self-consistent. So 16 plus 32 plus 71.1 plus 52.5. And I get 171.6. Almost hard to believe considering that we made so many approximations for fractions and so on.